Good afternoon, everybody. Welcome to the Triangle Quantum Computing Seminar Series. Since this is my first appearance as a co-host, I would like to introduce myself. I'm Eric Geisels. I'm a professor of economics at the Kenan-Flagler Business School and professor of economics at the Department of Economics at UNC Chapel Hill. I'm also the faculty research director at the Rethinc labs at UNC Chapel Hill. Up until the end of last year, I hosted a quantum fintech webinar series, which was a joint event of the Kean Institute at UNC Chapel Hill and the NC State IBM Q Hub. We have decided to join forces in the Triangle. That is to say that the webinar series that was exclusively on financial applications is now has merged with the Duke NC State quantum computing webinar series, and I'm delighted to be joining as co-host Ken Brown and Patrick Dreher, and obviously also highlighting the fact that financial applications of quantum computing are becoming increasingly more important. Today's speaker is a very prominent person in applications of quantum computing in finance. In fact, the very first webinar that I organized had Stefan Werner from IBM Zurich and Nikitas Stamatopoulos, who is giving a talk today as our first speaker, is also presenting actually a paper joint with Stefan. So this is great work. He is a vice president in the R&D Engineering Division at Goldman Sachs with research focus on algorithmic development, resource estimation, and application of quantum computing in finance. Prior to Goldman, he was at JP Morgan, focusing on high-performance computing solutions for quantitative problems in derivative pricing and portfolio optimization. And from 2018 till 2020, he was leading the investment bank's research in quantum computing. Nick holds a PhD in physics from Dartmouth with focus in field theory and cosmology. He has shortened a little bit the title of his talk. Nick, it's all yours. And I'm looking forward to your presentation. Just a little bit of housekeeping. You can write a question in the chat, or if it's just a clarification question, please feel free to ask it during Nick's presentation. Thank you very much, and welcome, Nick.
Yeah, thank you, Eric. Thank you for having me. Thanks, everybody, for organizing this webinar. I'm happy to be here. I'd like to talk to you today about the recent work that we did, and I was quickly highlighting. The preprint of which went on archive towards the end of November last year. The title is Towards Quantum Advantage in Financial Market Risk Using Quantum Gradient Algorithms. And this is work done in collaboration with IBM Quantum. The quantum research team at IBM located in Zurich, and our team at Goldman Sachs. Maybe a little bit about our group and how we as a firm see quantum research, what we're trying to do, and how we're trying to deliver some value to the bank. So our way of approaching quantum research is in a let's say backwards way. So we work in a backwards manner. So we start from a problem that we know we need to solve classically. We take the algorithm that is of promise from a quantum point of view, and we try to see, what kind of a quantum computer do we need to deliver advantage for that particular problem, whatever that advantage is, right? In some cases, we just want to solve a problem faster now, well, with a quantum computer than we can do with a classical computer. In other cases, perhaps we want to have a better solution, and maybe the time to solution is not the biggest concern. But one thing that is quite interesting in the field of quantum computing and finance is that financial applications, they often have like a close connection between a potential computational advantage and useful value from like a monetary point of view, right? So you can say, I mean, this is an easy question to answer, right? If you're talking to to the CFO or some other person, if we were able to do this calculation, twice as fast, what would that translate in dollar value for the bank, right? So there's in some cases that's a good thing to have, and we try to measure it in that sense, so we can measure our value. So we have this approach, but these applications, these financial applications, obviously they're not quantum native because we're dealing with classical data, and it's not there's no simple recipe that would say, well, here's what you do now, here's how you do it in a quantum computer. In some cases, there are algorithms, which is what we do, right? We take some algorithms and we try to adapt them to the specific instances of problems, but it's not a straightforward task that could be done in a straightforward manner. So perhaps the three key components of our work, and perhaps the first two are the most important, or the ones that we spend most of our time on, at least at this stage of quantum research in our group, is, as I mentioned, is the resource estimation. So what do we need for quantum advantage, which requires understanding how you're solving, well, what problem you need to solve. That's actually harder than it sounds. How do you solve it classically? How do you use a quantum computer to solve it? And what kind of a quantum computer do you need to get an advantage in compared to classical? So that's by resource estimation. And then algorithm design follows after that. So I've placed it next to it as if it's the second step. And it actually is the second step, because once we get the resource estimate, in the beginning, we get the crude number because it's not straightforward to do. Then we try to dig in and reduce the requirements of that we originally put together, either by clever tricks or by rethinking the algorithm, how it should work, the parameters of the algorithm, and all these tricks that we try to do to make to bring things closer to reality as far as quantum computing is concerned. And then the last point is, okay, well, it's one thing to talk about an algorithm, and another thing to actually run it on quantum hardware. Especially with the limitations that quantum hardware has in terms of errors, connectivity, and other things. And we try to imagine it in terms of a point in time where we're able to do error correction, and how we imagine we can do error correction, or how we can leverage specialized hardware to adapt particular applications of the algorithm. And we have a wide range of collaborators. We collaborate in industry a lot, with startups, with academics, and we do some benchmarking on quantum hardware. But admittedly, our focus is mostly on the algorithm development and resource estimation, just because we think most of the value will be in fault-tolerant quantum computing. At least that's something we do know, that there will be value. And with that, I want to give a quick kind of overview, at least how we see the progress of today's hardware and where those applications I'll be discussing stand, in how far away we are. So in this graph, I have the number of qubits that the quantum processor might have on the x-axis, and the program depth that the processor can run. And this is a little bit vague. I'm not trying to be very exact in here, but we can think of it as the number of instructions that you can run in a coherent manner on a quantum device. And obviously that comes with a lot of limitations. So you can think of some arbitrary line, this dashed line that we call HPC horizon, where you say, a classical computer will have a very hard time simulating any device that has more than 53 qubits here, which is kind of defined in conjunction with the quantum supremacy result by Google. There's I've highlighted the lower left corner, roughly what the capacity of QPUs today is, and in the near future, maybe it occupies this region. There's this in the upper right corner, we have actual implementation of Shor's algorithm and database search. The two standard algorithms for which we have proofs of doing better than classical. And there's this NISC era, which I'm sure a lot of you are familiar with. It's this era where we expect we'll be probing in the next few years, where we don't necessarily have provable speedups or advantages, but people have some hope that there will be something interesting that we can find here in terms of actual potential advantage in applications. Then I've highlighted a couple of results in the hardware space. So roughly speaking, this is where the Google result of 2019 is. There's this recent results from IBM about this the Eagle QPU, which I think is live. I'm not sure now, but essentially, the idea is that we take those as quantum hardware progresses. With these dots, they keep going towards going higher up and further to the right. Right. So that's what we imagine and hope that that will happen with the progress of hardware. And then on the other hand, there's this the application of derivative pricing using quantum computers, which is something our team benchmarked in 2020. We did a kind of a full end-to-end resource estimation about here's a particular derivative that the bank really wants to price fast with all the characteristics. Here's how long it takes for that to be priced classically. What kind of hardware do we need to essentially just break even, just to achieve the same performance as a classical computer or how it's run today? And we came up with this dot here, right, like this point, which is about 8,000 qubits and like 10 million or 50 million program depth in terms of like a T depth of the number of T gates that you can run exploiting parallelization. But this is a first estimate that admittedly was very hard to put together, and we had to do a lot of work to get that point. But as I mentioned, we think this is very important for benchmarking and these applications. And so we have another point now in this map, let's say, where building on that derivative pricing work, we tried to first of all see what other application can we tackle with the same problem, with the derivative pricing problem. I will go into the details about what Greeks is and what's market risk and all that. But what I want to highlight here is that we've made some progress towards reducing the requirements of qubits and how deep the quantum processor needs to be able to run. But I have to highlight here that the difference is it's quite small, and there's we made some optimization in the problem. It's not really this particular application that makes the requirements go lower in terms of the program depth and the number of qubits. So don't read too much into it. But this is what we want to achieve, right? We want to take these green points and bring them towards the bottom left, and the other way around with the red dots. However, even though I told you this distance here in this map is not that important for this application, we did achieve something that we think is quite a big step forward in terms of bringing an application or bringing the quantum hardware closer to where we could be in the near future. And that's the logical clock rate that the quantum computer needs to operate on to match the performance of classical computers. Right. So if we want to say that we can price a derivative faster using quantum computer than classical, then you got to take that into perspective. And if you have some amount of instructions you need to run them at a particular speed that in order to match the performance. And in our first iteration, that number was 50 megahertz of logical T-gate execution. And that's a very high number. And now with this work we did on top of that, we managed to bring the number down to 1 megahertz, which is still quite high for what those numbers are now. We don't know really what the future will bring, but this is just a benchmark we did with a small sample, with a small problem, right? So if we take a realistic problem that is used in business right now, we expect that this number would go down. But this is something really promising, and we're really excited about. Okay, so hopefully I've set the kind of the state here of where we are, what we're doing, and what we're trying to achieve. So let me dive in some derivative concepts. Hopefully, most of you are familiar with derivative pricing and the basic ideas of derivatives. Just quickly going over the definition. So derivatives are just financial contracts whose value is derived from one or more sources of uncertainty about what the market will be in the future. The simplest example you can think of probably is a simple option on one underlying asset. So an option is a contract between two parties where an agreement takes place today of a possible future transaction with parameters decided upon today. Right. So one example could be that in 6 months from now, you have an option to buy from me some particular asset X at some price Y, and X and Y are agreed upon today. And the question that derivative pricing tries to answer is, how much is this contract worth today? Right. So if I give you the option to buy that asset, how much should I charge you for you having this option? So this is a contract, right? This is something that that is tradable, and this is what derivative pricing tries to answer. Now, there's a lot of theory about how to price these contracts, and there's a lot of details which I think it's beyond the scope of this presentation. But loosely speaking, let's just we can talk about some very basic definitions. So you can think of every derivative type to be associated with some function that we call a payoff, f, which is defined on a domain of some stochastic variables. And traditionally, the way that we price these derivatives, if it's not something very simple, and usually the realm of derivative pricing that we're interested in is the non-simple cases, what we do is we make a model about how we think the market behaves in time. We simulate a large number of paths for all these stochastic variables that enter our calculation. And we approximate the price of the contract by computing the expectation value of the payoff on each of these paths as an average, right? And there's there's a lot more things that go in there. There's you have to take discount things. You have to adopt a risk. In some cases you use a risk neutral measure, but you have to adopt some kind of probability measure. But in terms of the computational aspect of it, you can just imagine as I just generate possible paths of asset prices and anything else that enters the calculation, then compute the payoff function on each of these paths, and then create an average, and I approximate my price as that. So the example that I talked about, the simplest derivative, which is a European call option. Essentially, we agree on a price today about a possible transaction in the future. So let's take an example that from the previous slide, that in 6 months you have the option to buy a share of IBM from me at some price K that we agree today. Then in 6 months, if the price of IBM stock is S of T, then your payoff, or how much you're to gain from that, is the difference between the value in the market and what you can buy it for from me, right? So you can buy it from me and sell it in the market. So that's what you gain from that. So you can express it. You can express usually the payoff of a derivative as a simple function usually, right? But it can become very complicated. And obviously this is a very simple example. This is not what we try to do with Monte Carlo, but I thought I'd include it as the proof of concept, so to speak. And not only is this a simple example, a simple option, this is also path independent. And in general, path independent options are very easy to price, even if they don't have closed form solutions. So we focus on hard to price path dependent derivatives, meaning that, so if you're seeing this graph, in the simulated asset prices, we don't just pick one instance in time. So the x-axis here is time in some dimension. you don't just pick a slice here, but you have to take into account the whole path, and there's a value going there from all the path. Right. Okay. So then, to put it in a little bit of more formal context, we can think of these more complicated derivatives. Again, simplifying a bit, but putting a little bit more complexity. We can think of a contract, a derivative that's defined on D underlying assets. And at each time t, we have a d-dimensional vector of asset prices that we call S, right? Indexed by t. Then we can think of a collection of these d-dimensional vectors representing different snapshots in time of asset prices that that the derivative is based on as a path. Which we can call omega, and we have with our modeling we have a way to ascribe a probability p of omega to each path omega, and that's where the modeling part comes in. For this purposes, it's not that important, but we do have a path omega. We have a probability of that path p omega. Then we can define g omega as the discounted, the payoff of the derivative contract we're interested in on these assets. So this is the value that the contract has on that particular path. And then we can approximate the derivative price as the weighted sum of the payoff evaluated on each of these paths, weighted by the probability that we ascribe to that path. Right? And this is how we do it using Monte Carlo. In Monte Carlo, we don't really put the probability for a path. We generate the path given the probability, but we can kind of turn this around a little bit depending on the model. So this is very equivalent, really, of how we do it classically and quantumly. At least what we define as the price of the contract. And the key point is the reason why we're focusing on derivative pricing is because quantum amplitude estimation can give a quadratic advantage in error scaling over classical Monte Carlo. So if you want to approximate this derivative price, which is the expectation value of the payoff, if you have a target epsilon, I want to be epsilon close to that value, then the number of paths you need to take from Monte Carlo goes as 1 over epsilon squared, whereas the quantum equivalent goes as 1 over epsilon, right? And what we did is, in our previous work, is that we estimated resources for advantage for 2 particular types of derivatives, and this is where those numbers in that graph came from, right? This 8,000 qubits and 5 times 10 to the 7 t depth, and this is just a proxy for depth. Okay, so the derivative pricing part is not the most important or what I want to talk about here, but I need to give some context here. Essentially, there are 3 components. You need to come up with a way to load this stochastic process. Essentially, for a path omega, you need to find a way to encode the probability omega as an amplitude somehow. You have to come up with a quantum circuit to evaluate the payoff of the derivative and encode it as an amplitude. So you have something like this, right? And then you have to use amplitude estimation, which is the quantum algorithm, which allows you to read out the number that you're interested in, which is the sum over all paths of the probability of each path times the payoff of each path. And perhaps, one thing that I want to make, quite clear is this, right? So what the first 2 components that I've boxed here is, let's call it the pricing operator, right? So load the stochastic process, apply the payoff circuit. This is quite easy to do in terms of computational resources, complexity-wise, right? So, I mean, you got to figure out how to do them, but once you do that once you apply this box once, you've already calculated the number that you want. The number that you want, this expectation value, is already somewhere in the quantum chip, but it's encoded as an amplitude essentially, or a probability that you can't just read out, right? And amplitude estimation is applying this pricing operator over and over and over, 1 over epsilon times, to just read the number out. So computation of the number is not hard, relatively speaking. Reading it out is hard. So intuitively thinking, if you do have the number already in quantum memory, you might as well do as much as possible with it while it's there before you read it out. Right? So kind of increase the expectation or increase what the classical computer has to do to be on par with the quantum computer before you make it complicated or before you add the complexity from the quantum computer. That's, you know, if you get nothing else from this talk, but this, I think I'll be happy. You know, you've done the hard work, you might as well do more. And that's why we're looking at this particular problem, which is this concept of market risk, or Greeks, loosely speaking. Right? So we mentioned that we have a derivative price in this form. Now, if you compute the gradients of the derivative price with respect to one of the market parameters that go in the calculation, for example, if you have a derivative on multiple assets, one of the assets price is a parameter. You know, what is that value today? What's the volatility of the assets as I estimated today? What is the interest rate for some particular maturity today? These are all inputs to the derivative pricing problem, and the gradients of the price to these parameters, they're known as Greeks. They're called Greeks. So I'll use that for simplicity from now on. So as I mentioned, you know, the simplest thing you can imagine is if you have a derivative on a single underlying asset, you can compute the sensitivity, right, the gradient of the price with respect to that to the price of that asset. And the reason why we're focusing on this is that these are actually quite important and they play a very big role in the computational cost of derivative pricing in banks. And one of the reasons, maybe the primary reason, is the fact that a lot of hedging traditionally happens through Greeks. So you compute how sensitive your contract is if the market changes, and you try to take offsetting positions so that you kind of hedged, you know, if something goes bad, right? Or you want to lock in some kind of risk in your contract. Okay, so then, so how do we compute these Greeks, right? So if you're pricing your contract using Monte Carlo, the simplest thing you can do, and what's been done traditionally, even though there's some clever ways to go about it, you can just use classical finite difference and compute an approximation to the gradient just by pricing the contract multiple times, computing a small Taylor expansion properly truncated. And that goes as k over epsilon squared, where k is the number of Greeks that you want to calculate, right? And this just says, okay, well, I will need to price the contract at least once for each Greek I want to calculate if I want to define a difference. Each Monte Carlo calculation goes as 1 over epsilon squared, so I get k over epsilon squared. Right? That's straightforward. Now you can have another approach, which is called, we call it, I don't know, somebody called it semi-classical. So you can still use a classical finite difference, but you price the contract quantumly with amplitude estimation. And since amplitude estimation can do it as 1 over epsilon, that becomes k over epsilon, right? So that's something you can do right away if you can, if you have a way to use amplitude estimation already. And the question is, can we use quantum gradient methods to improve the scaling with k, right, with the number of Greeks? So we already have a benchmark of k over epsilon. Can we do better with k, right? And quantum gradient methods, I'll describe right now what they are. And I'll first draw a parallel here. So let's say that you want to compute the gradient of a function f. And so f is a scalar function, it's in one dimension, and you want to evaluate the gradient at the origin here, right? At this red cross here. So what finite, one particular central difference method or stencil that you can use here is say, okay, well, just evaluate the function f at some distance L away from, in both directions, away from the point you want to evaluate the gradient on, and then compute this expression, which will give you an approximation for the gradient. And this is just, just by doing Taylor expansion, you eliminate some terms, and the error terms here, they go as L, L squared here, so that you can get, you can start eliminating the higher order terms, or reducing the impact of higher order terms by choosing L being small. Right? So what you want to do is that you want to use a region L where L is very close to this point, and the function is approximately linear there, right? So you don't want the higher order terms to spoil your estimation. And this parameter L controls the accuracy of the approximation, right? So you need to pick that carefully. So this is how you do it with classical finite difference. This is not obviously the only way that you can do it. There's higher order stencils that you can use. So instead of evaluating the function twice, you can evaluate it 4 times and combine them in a clever way so you get rid of higher order terms, or 8 times, or I mean the process doesn't really end. You can just pick whatever order you want your stencil to be accurate, and you can find a better stencil classically. But obviously, the more times you do that, the more times you need to evaluate the function. And this is where the hardness of the problem is, right? You want to minimize the number of times you call the function f. Okay, so just use this as a proof of concept. Just imagine this. Now, what a quantum gradient does is that it operates in a very similar manner, or it relies upon evaluating the function in a region that's small enough where the function is approximately linear. So this is the common theme between the classical finite difference and quantum gradient methods. However, when you're using f, when you're evaluating f as a quantum function, you don't really need to evaluate it individually at 2 points. What you can do is that you can create a superposition of inputs and then evaluate the function on all these inputs simultaneously, right? In that superposition. And this is the fundamental point of quantum gradient methods. What it does is that it still uses a region L where the function is approximately linear, and then you use a number n of points that you evaluate the function on using superposition. And the one thing, or qualitatively how to think of these parameters, the size of L controls the accuracy of the approximation, just like it does classically. Like you need to pick this region to be small enough so the higher order terms, they do not interfere with your estimation. But in the quantum gradient method, you have another parameter n, which controls the precision of the estimate, right? So the higher n is, it means the more points you evaluate the function on, which means the more qubits you have involved, but that allows you to read out the result more precisely, right? So you want to have a small n, and you have a small l, and you have large n. And that's I just want to give you this view of what the gradient algorithm does, which I'm about to go now into more detail. And essentially, this algorithm in its first form, it was put together by Stephen Jordan in 2005. And essentially, it says that let's say you have a function f, which has a k-dimensional domain, and it's a scalar function. Then let's say that given some point x in this k-dimensional space, and some scaling parameter s, which I'll leave it vague for now, but we'll go into what this is and why we need this. Let's say that you have an oracle of this form, a quantum oracle, right? So x is the input point, and what the oracle does is that it leaves x the way it is, and it computes the value f of x as a phase, and you have the scaling parameter s, right? So assuming you have something like this, then do the following. Okay, so now we just saw an example in one dimension, right? But this this extends to obviously a large problem of large dimensionality. Now let's imagine you have a point x0 that you want to estimate the gradient at. Then take a k-dimensional hypercube, right, of n different points. So perform this, pick some L, just as previously, and cram n points into that region L in every dimension, and then evaluate the oracle on that superposition, right? And all these points, they need to be in a superposition, right? So on the left-hand side here, you can think of these deltas. These are points around the point x0 where you want to evaluate the gradient on. So delta are these points, which we can call this hypercube G around x0, and it's k-dimension, right? So you can initialize this superposition and then evaluate this oracle, which what it does, given the definition of the oracle, we get something like this, right? So you have in the phase, you have f of x0 plus delta, because we can represent delta as deviations from x0. I mean, that's just the nomenclature here, but we can have these deltas be deviations, right? So this is more clear to understand. And once you have here, then if you've picked your parameter L small enough so that the function f is linear between x0, approximately linear between x0 and these deltas, or the maximum delta, then you can use, so you can just use the Taylor expansion, and then you get the gradient out of f of x0 plus delta, which comes out as a global phase, and we can ignore, and we're left with the gradient times this displacement delta, right? These different points. And if you notice, we can apply an inverse Fourier transform in this original superposition we created of these deviations delta, and what we read out is essentially a multidimensional gradient, right? Or the entire gradient, and we can think of it as the gradient in each dimension with accuracy n. That's why n comes in here, you know, and this is the accuracy of this will be related to how accurate this approximation is. So this is the basic idea. It's a very simple algorithm, right? I think it was left alone for a while. I don't know if it got too much attention, or I don't know if people put too much effort in that. I didn't see that much, but perhaps I've missed something. But the problem is, or the question is, okay, that's very nice, right? But what is how do you compute the gradient with some guarantees about the complexity? You know, how does it scale? What is the error? What is the accuracy and precision of these estimates? And the first kind of coherent or rigorous approach to examine the complexity of this algorithm was done by this paper from Gillian et al. In 2019, which showed that the required scaling, so this S factor that I've purposely left undescribed before, it needs, in order for this algorithm to work, you need to pick it as n over L, right? Where n is the precision estimate or parameter, L is the accuracy parameter. And that goes as square root of k over epsilon squared, right? And if you recall, our target was to find something that does better than k over epsilon. So it does better than k, the square root of k, but now we got the epsilon squared again. And this is obviously not something that we want, and that's what this paper realized. So what they did is that they introduced a family of higher order oracles, where they take advantage of higher order stencils, approximations for gradients, just the way you calculate them classically, and then you use them to encode these stencils in the phase and get rid of higher order terms that contribute in the error that accumulates in this algorithm. So for example, so this is the oracle that was in the original paper, right? So you just evaluate f of x at the point x. The second order oracle has this form, where for each point x, you compute this linear combination, f of x. So this is assuming that you want to compute the gradient at 0, which you can always do by rescaling. But let's assume we just compute the gradient at 0. So x is a deviation from the origin. You evaluate it at x and minus x, and you have to figure out the correct coefficients a that give you this good cancellation of higher order terms, and this will do a better job, right? As an oracle, it will do better than square root of k over epsilon squared. And what they did in that paper is that they proved that for a certain family of functions satisfying some smoothness conditions, which is not quite important for our presentation here, essentially it puts some bounds on how big the high order gradients are for the function. Then they prove that they can get a scaling of square root of k over epsilon. Right? So they get back the 1 over epsilon convergence, and you have a square root of k instead of k. Okay, so now the thing is that in derivative pricing, at least, we don't really know. We don't have a closed form solution for the functions, right? So it's kind of hard to say if these smoothness conditions apply for our algorithms. And the complexity here scales, obviously, for this family of algorithms, the more terms, stencil terms you take, the more the complexity, the higher the complexity becomes. And then you have the scaling with the accuracy parameter L and N, as we discussed. So what we did is that we tried to simulate this algorithm or this family of algorithms with some derivative contracts that we have in mind. And we want to see, numerically, what are the resources that are needed to use this quantum gradient algorithm to compute the Greeks, and compare to what these parameters are for this from the proof of this theorem that guarantees the square root of k over epsilon. Right, and there's a number of questions that we try to answer about this quantum gradient methods. So first of all, can we actually apply these gradient methods for derivative Greeks? And the idea is that, as I mentioned, the original Jordan algorithm requires an oracle which computes the value of a function if you're interested in f of x as a phase. What we have in derivative pricing is a probability oracle of this form, which encodes the value into the amplitude of a particular state. So this is called the probability oracle. And the question is, can we get one from another? And in that paper, the Gillian et al., they show that we can create a phase oracle from a probability oracle using techniques around block encoding and Hamiltonian simulation, which I don't want to go into too much detail about what they are, but there are some complexity arguments that this is an efficient operation. Now, how efficient, it's not really worked through. We worked it through in our paper and have precise numbers of how many times you need to invoke this oracle, this pricing oracle, in order to achieve to do the Hamiltonian simulation and get the phase oracle, which is our goal, right? With the phase oracle. So we did all this calculation, and so we were able to take some example and figure out what those numbers are, so we can compare it with the theoretical expectations from the smoothness condition theorem. And then we tried a couple of examples. So we did numerical simulations of that algorithm. First of all, with the European vanilla option, because we have a closed form solution and we can benchmark it quite well. We can compute the Greeks analytically. And then we want to see, okay, if we do well, what are the parameters that we get numerically and how do they compare to the theoretical expectations? So the simulation, it showed that, at least for this vanilla, this very simple option, it's quite easy. You can do it pretty well. And the important point is that the parameters that we found numerically, they're much more beneficial or much less daunting than what the theory suggests. So if you can see here, each row in this table, it says how many Greeks do we calculate simultaneously, because this is a batch calculation, right? You compute all of them at the same time. So the more, so each row, we compute 2 Greeks, 3 Greeks, 4 Greeks. M is the order of the finite difference approximation that we encode in the oracle. So the lower this is, the lower the cost. L is that linearity parameter. So you see that we're able to find M that is smaller than what is expected from the proof of the smoothness conditions that are required for the square root of k convergence. The values of L are quite large, which is good for us. And you can see the cost in terms of how many times we need to invoke the pricing operator, which is how we measure cost anyway, is about 2,000 invocations, whereas what you expect from theory, it's about 600,000. So there's a big difference there. But this is a very simple example, and we don't even need to do Monte Carlo or anything else to compute these. So we switched our attention to something slightly more complicated, which is actually a type of contract that we do price in day-to-day operations. This is probably not that important either, but essentially we have multiple underlying assets. The payoff is a linear combination of these assets, and it's path dependent because it's it only goes into effect if it crosses some particular value at some predefined instances in time. But we don't have a closed form solution for this, and we need to do Monte Carlo to solve it. So we tried the algorithms in this for this example as well. Now, as you can see, compared to the vanilla example, the vanilla European option, the precision that we use here is much worse, because in order to simulate this, we need to do a Monte Carlo for each point in the superposition for each Greek. So this becomes quite heavy. And what we do see is that we still see a big discrepancy between the numerical results that we see of the cost of the algorithm and what is expected. So 1,600 compared to 200,000. And that's for 4 Greeks, right? And again, the number of Greeks and the precision that we're able to simulate is because of limitations of compute, because you actually need to, to do exponential size simulation on classical hardware. And so, this was the result that indicated to us, that's a useful thing to look at. You should look at it more closely. We have a good number here, 1,600 compared to 200,000 for the oracular cost. But let's see if we can do better. And what we did is that, we realized that Hamiltonian simulation is the most costly component. So we tried to see if we can come up with a way that avoids Hamiltonian simulation in order to create this phase oracle. We have 10 minutes. I'll go very quickly through the last slides. I'll just highlight the important points. We found a way which is just a straightforward extension of amplitude estimation oracles with a few tricks to make it work. But we found a way to create a second order accurate oracle, phase oracle, which does not rely on Hamiltonian simulation. And you can read the paper for a few more details. But essentially, what we can do is that we can compute, we can use the quantum gradient algorithm to compute the gradient of this quantity theta of x, which is related to the function f of x that we have. So computing the gradient of theta of x, we can actually compute the gradient of f using this relationship. And there's a particularity about the sign of the gradient, but we have a way to distinguish that as well. But long story short, given that we're able to do that, the simulation, this is a nice little circuit. Let me go through the results. Yeah, so we can use this simulation-free approach algorithm. And we tried it on this basket option that I mentioned before. So it works quite well, or as we expected. And if you look at this number here, the simulation-free method for these 4 Greeks, the number of times we need to invoke A is 64 to achieve the same accuracy as the rest in this table. So we picked some accuracy, which is actually limited by how much we can simulate it. I think in this case is 1/16. Is that right? Yeah, because we use 4 qubits per dimension. Yeah, 1/16. And so we measure the parameters and we see there's a big, now theoretically we expect if we run this algorithm to take 200,000 times invocations of the pricing operator. Then numerically we find with Hamiltonian simulation, we have 1,600. But if we use the simulation-free method, we get 64, right? And it's interesting to see that if you just use a semi-classical method for these 4 Greeks, you get 256. So even a semi-classical method does better than the numerically estimated quantum gradient method for 4 Greeks. But as you expect, this should, for more Greeks, the GAW, sorry, I didn't define it. This is the quantum gradient method named after the authors of the paper that put together that family of algorithms. So we're quite excited about this result. What we ended up doing after that is we invoked some maximum likelihood estimation methods to turn the quantum gradient estimation algorithm into an end-to-end algorithm with precise confidence intervals and probabilities. And this was quite neat. This is also used in standard amplitude estimation, in some forms of amplitude estimation. And one thing to keep in mind is that at the end, when you apply the quantum gradient method, the probability distribution you get is very much like quantum phase estimation. So you can apply similar techniques. So there's nothing too new here. I mean, this was developed as part of iterative quantum phase estimation from IBM, and a straightforward application to this algorithm. It gives us a pretty nice end-to-end algorithm. which we can simulate and get exact results and costs. So in this case, we're using this MLE method to estimate the vega, which is 1 Greek of the basket option. And you can see the red dashed line here is the correct result, or I mean, you have to do it with Monte Carlo. So, but it's we try to estimate it with like 1 million paths. What is the we call it the exact or analytical result. With MLE, we can get this point, this green point here, which is quite close, and it's better than it does better than measuring and picking a median, which is the approach that was considered up to that point. And as I mentioned, I showed you in that graph, we can come up with some numbers about how does this change the resource estimation for advantage in finance. So the number of qubits and the number of T gates that we need, they're more or less the same. There is a little bit of they're a little bit better than our previous estimate because we've made a few optimizations. But the key point is that with this algorithm, we calculate 4 Greeks, so the classical benchmark increases. Classically, you have to price them individually, right? You have to price each one individually. But in the using the quantum gradient method, you can essentially read them out and take advantage of the fact that you have the number you've calculated in memory. So this additional processing I mentioned at the beginning is calculated in these Greeks, right? And you know, one important point is that we only calculated this for 4 Greeks because of computational resources. You would expect that, or you would hope that this algorithm would do much better as you increase the number of Greeks, right? The question remains, though, you know, the derivative pricing function, if you were to think of it as a function end-to-end, where you tweak the parameters and you have a value for each point, you know, how smooth is it? What kind of gradient order of stencil you need to use? And how does how does it generalize to this large number of Greeks that I mentioned? So you might need to compute 1,000 Greeks, you know, for day-to-day operations or something like that, of that order. So you can imagine if there is an advantage to be had here, it's quite significant. And so just a quick summary and just a few points about looking ahead. So considering this derivative pricing problem at the higher level of aggregation, as we found out, it can deliver additional speed up or decrease the resources that we need for advantage. And I think this is a very key point here. You know, pricing is an individual contract is not really the end goal, right? When we say Monte Carlo is expensive and in the banks we simulate, you know, millions, we have millions of contracts and all this stuff, is because we're interested at a much higher level of aggregation. We want, let's say, we want the Greeks of a portfolio, for example. Like even this example I studied, it's very basic, right? So we need to think, from my point of view, we need to think from a more global level or a higher level of aggregation to deliver additional value, to get additional value from a quantum computer. And then the things I mentioned, you know, how well do these algorithms perform for a larger number of Greeks? For example, the simulation-free method that we developed is we only know a way to do it for a second-order accurate stencil. So we don't know, you know, how well it will do for more Greeks, but at least we have this benchmark. So, you know, maybe some of you should take a look and try to extend that so you can make, without having Golden simulation, make a better stencil. That would be awesome. So yeah, so can we construct simulation-free oracles for higher orders? And if not, or even if we can we reduce the cost of Hamiltonian simulation? Because at least there, if we have Hamiltonian simulation, we can do whatever order we want. It's just expensive. So if we can reduce that, it will be should be fine. Okay, and with that, I think I've gone through most of the material I wanted to go through today. There's 3 minutes. Eric, I don't know if there's any questions, or I'm happy to open it to anyone.
Yeah. First of all, thank you, Nick. This was this is a lot of good stuff. Thank you so much. There are 2 questions in the chat, one on high frequency trading and one on quadratic versus polynomial speedups. Let me just start. Do you have access to the chat? And I'll just
no.
read for you. There's one from Dror Baron. Thanks for the helpful review. I imagine that a quantum computational advantage would likely be for slower trading approaches and not high frequency trading, because high frequency trading already works in sub-millisecond times. Is my hunch correct?
Yeah, probably. I mean, if the type of calculation that you're interested in is in the millisecond range, then I think that's correct. I mean, you never know what kind of quantum computer we'll have access to, but that's not, the most favorable bet if you were to bet. But I mean, in high frequency trading or in other areas where you try to estimate or find a signal or come up with a strategy, there is some work that draws some parallels between time series analysis using quantum computers and this topological data analysis. There's a lot of things that you can do there. Perhaps in that space, high frequency trading approaches could benefit from quantum. But in what you say, from reading the book data to submitting an order, I doubt the quantum computer, or it doesn't look likely, will be able to help you there.
Yeah, I agree. I mean, from a finance perspective, this is more about taking portfolio positions and evaluating portfolio positions at a lower frequency, not so much actual trading. The second question is from Nikitas Stamatopoulos. Thank you very much for this algo of it's about the quadratic speed up. So arguing that most of the speed ups in finance applications have been of that quadratic nature. And what about sort of seeing exponential speed ups under some conditions? Quadratic is very good, but would you say there is any hope for a better than quadratic speed up for finance algorithms? That's sort of a question that is, I think, came up in some of the other talks actually as well. And I mean, what's your thought? What's your take on this?
Yeah, I mean, that's a question we would all like the answer to, know the answer to. I mean, there are some, I mean, we have some ideas about exponential speedups, but how they relate to finance is not straightforward, right? So you can use HHL, right, to get an exponential speedup in some linear systems,
right?
But you get you get an answer which is encoded in a quantum system, and then you need to do some kind of tomography, or like you kind of negate the exponential speedup just to read out the numbers, right? Which comes back to the same point of reading out the numbers. There are some ideas, I think. But let me mention one thing actually from this talk, right? So the classical algorithm to compute k Greeks is k over epsilon squared, right? It scales with k if you use finite difference. The quantum algorithm, that it has a complexity proof, it goes a square root of k, right? And it has some smoothness bounds conditions on the function. Now, if your function is linear in every dimension, then the quantum algorithm performs as 1 over epsilon. It becomes independent of k, right? So I don't know what you call that speed up. I mean, you depend on k. It becomes constant, right?
Yeah.
But obviously, I mean, that, you don't deal with linear functions, but there is a range there, right? So with the simplest function you can imagine, you have constant cost for the k Greeks. It doesn't matter how many Greeks you want to compute. Then we have the square root of k, which is with some smoothness conditions. And obviously, clearly, we're somewhere there, right? I mean, okay, we could be worse than those functions. So we're not as smooth, so the square root of k doesn't apply. But we could be somewhere in between, right? So that's why I think this is quite interesting problem, because we don't really know. It's not, first of all, like we can barely describe as a function a payoff, right? If you think of derivative payoffs that rely on optimizing some surface and then finding some, I mean, payoffs can be complicated as they are. If we think of the overall price, right, as a function, then it's very hard to estimate for this problems, how smooth they are, or how do you even measure that. I don't know. But I just wanted to leave you with that there is, even in this problem, there's a range where we could be super quadratic. I don't know. Something.
Yeah. In the interest of time, I would love to keep talking, but we can do this offline. Thanks you so much, Nick. This was a really great talk. It was an inaugural talk for this joint new seminar series between the three universities. I also would like to thank every participant for staying with us this afternoon. And from what I understand, just visit the webpage. I think, Patrick, you want to say something? Is that correct? Am I misunderstanding your hand up? Or
no. I was just applauding the speaker.
Thank you very much.
Yeah.
Please visit the website for the next events in this series, and have a good afternoon. And I understand we're going to have another storm coming through, so stay safe.